Hello. I want to return to solutions to the three-dimensional Schrödinger's equation. So previously we had looked at separation of variables in the r and the t directions in space and time, and then also considered separating in space, pulling out the radial coordinate and the angular coordinates in spherical coordinates. And we ended up with the radial equation and the angular equation for solutions to the three-dimensional Schrödinger's equation. And what I want to do now is focus on the angular equation. So let's dig into this a little bit more. So our angular equation depends on both theta and phi. And so we're going to do yet one more separation of variables where we're going to separate our angular coordinates into a product of a function that depends on theta and a product that depends, or a function that depends on phi. And we're going to insert that into our expression for y everywhere we see y in the angular equation. And then as usual, we'll divide by theta times phi. This is the usual story in separation of variables. And then we will get two equations for theta and phi separately that we can then solve as ordinary differential equations. So let's insert this expression for theta and phi into the angular equation. If you do that and then divide by theta times phi, okay, skipping some of those algebra steps here, you get an expression that looks like this. And I've colored in red the terms that depend on theta, and in blue the terms that depend on phi only. Usually the next step in separation of variables is to define a separation constant, because after all, the terms in red are only functions of theta, the term in blue is only a function of phi, and the only way that this equation can therefore be satisfied is if, say, the term in blue, which is in principle a function of phi, is not a function of phi at all. In fact, it's just a constant. And so we have to have that term be entirely a constant, and that's what we define as our separation constant. So I'm going to define that as my separation constant, and looking ahead a little bit, I'm going to define that separation constant as minus m squared, because I'm anticipating what the solutions are going to look like. So then I get from this a theta equation and a phi equation. So let's see what those look like. In the theta direction, or theta equation, plugging in minus m squared for that blue term, the phi dependent term, and rearranging just a little bit. I'm going to move the l plus 1 over to the left, and then the m squared over to the right, multiplied through by capital theta, the function. I get an equation that looks like this for theta. Now, that doesn't look particularly enlightening. It, in fact, looks a little scary, but it turns out that solutions to this differential equation, this ordinary differential equation, are known. And the solutions are some special functions. And in fact, they have a name you may have seen before. So the solutions are given in terms of what are called associated Legendre functions. And the associated Legendre functions are called that way because they're associated with Legendre polynomials. And so it turns out that these associated Legendre functions are derivatives of Legendre polynomials times some power of 1 minus x squared. And again, remember, when we write something like PLM as a function of cosine theta, that means in a Legendre polynomial, if you see an x, you should instead write cosine theta. But of course, we can't keep writing it in terms of cosine x just for brevity, and so we just turn that into an x so that it's a little bit easier to write. We're going to return to these associated Legendre functions in a little bit and put them together with the phi equation. But for right now, we should just know that there are solutions like this, and we can work out what those solutions are, and we'll do an example. How about in the phi direction? Well, the phi direction, or the phi equation, we can pull just from that separation constant ansatz there and rearrange it by multiplying by phi. So I have the second derivative of phi with respect to the coordinate phi is equal to minus m squared times the function phi. Well, solutions to this shouldn't be hard to guess. In fact, solutions are complex exponentials. I'm just going to write it in terms of one complex exponential. It's the standard thing to do. And then allow m to be either positive or negative. And that will include both possible solutions to this differential equation. And so the m values are going to have to be positive or negative integers in order for things to make sense, of course, phi goes from 0 to 2 pi, and so as it comes back to 2 pi, the whole wave function should return to the same value again. And so you have to have integer values of m because of that. Okay, so we took our angular equation, we made a separation of variables ansatz for that angular equation by separating it in terms of theta times phi, functions that is, plugged those in, and extracted two equations, one that just was in terms of theta, and another one that was just in terms of phi. And the equation just in terms of theta had these solutions which were special functions, associated Legendre functions, and the solutions of phi were nice complex exponentials. So let's go back up the chain then and put this together. So now we have theta and phi separately. What we really want are the solutions y, and so let's multiply those together. So we multiply theta times phi, so that our solutions, I'm now going to write that in terms of y Lm, because it's determined by these two constants, L and M, are equal to some normalization constant, which we're not going to worry about here, e to the im phi, and then PLM of cosine theta, that associated Legendre function. These quantities here are what we call spherical harmonics. And spherical harmonics show up a lot in physics. They usually show up whenever you have spherical symmetry involved and you're interested in what's happening in the angular coordinates of spherical geometry. We already talked about there are these two integers, L and M. Let's dig in a little bit more to them. So L is oftentimes called the azimuthal quantum number, and it takes on positive integer values, 0, 1, 2, and so on. And then M is oftentimes called the magnetic quantum number. Now, just from requiring the wave function to come back upon itself as phi goes from 0 to 2 pi, you could imagine M could take any integer value, but it turns out it's a little more restricted than that. And the reason it's a little more restricted to that is let's take another look at those associated Legendre functions again. So those associated Legendre functions depend on both the integers L and M. And we notice that L shows up only in the Legendre polynomial. It tells us which Legendre polynomial to pick. M shows up in two places. It shows up as the exponent of the 1 minus x squared, but it also shows up as the power of derivative we're going to take of the Legendre polynomial. Now here's the thing. The Legendre polynomial for a number L is an nth order polynomial. For instance, p sub 1 has x to the 1, p sub 2 has x to the 2, and so on. I mean, that's just generally true of the Legendre polynomials, is that they're nth order polynomials. So now imagine taking an m which is larger than L. That means you'd be taking a derivative, d by dx, of an order larger than the polynomial of the thing you're taking a derivative of. Well, it doesn't really matter what the coefficients are of that polynomial, the derivatives are going to vanish. So if the power of this derivative is larger than the order of that polynomial, well, you're just going to get 0 because the derivatives will ultimately end up with giving you 0 for your when it acts on your polynomial, because it's an nth order polynomial. So that actually tells us that while in principle the m integers could have been anything we want, in practice, if we want a non-zero solution, then we have to have m be restricted to be between negative L and L. Okay, so this was a brief introduction to the idea of spherical harmonics and how they come out in three-dimensional Schrodinger's equation. And in the future, we're going to try and look at some examples of calculating spherical harmonics.